So with our benzene structures, we looked at aromaticity. I'm not going to go over that again, but ultimately our biggest section with the EAS or with the aromatic chapter is looking at EAS reactions. So your electrophilic aromatic substitutions. Okay? So the new functional group that we're addressing in this chapter is your aromatic ring, okay, or the arenes. So if we drew out an example aromatic ring, for this case we've got benzene. It's the only one I'll expect you to react, so it's 6 carbons with our pi system. Okay? Those double bonds we might expect to react similarly to an alkene because we've got electrons in that pi system. However, due to the conjugation, as in we're closer to other pi bonds, all of those pi bonds end up reducing their energy and becoming more stable, which means this structure becomes incredibly unreactive. Okay? It wants to stay as the aromatic ring. It does not want to react, which means when we do force it to react, its chemistry ends up being different from that of the alkene. Okay? So our similarities, our aromatic ring is a source of electrons. If we have a source of electrons, how might we expect it to react? Could act as a nucleophile. How else could it react? Could react as a base. Okay, so there's a variety of different things here. The base chemistry, as far as Bronsted-Lowry goes, doesn't work in the case of the aromatic ring. Okay, it does not want to pick up a hydrogen. It's not basic. It'll only react as a nucleophile. Okay, hydrogen ion is not acidic enough or not positive enough to react. Okay. So, if it reacts as a nucleophile, we would expect it to react with an electrophile. Okay? So we've got our electrophile in this reaction as well. If we were going to do something that we would suggest from alkene chemistry, we might expect an addition reaction. However, as the name alludes to, we don't see addition, we see a substitution. So when we go through and look at the product of our reaction, we end up substituting our hydrogen ion for the electrophile. Okay? Where this becomes tricky is hydrogens are often implied, just like for our elimination reactions. So you may not see that hydrogen there. You have to remember that it is present, that it is there. So go back and look and evaluate wherever your reactions are occurring and try and predict and see what's happening with them. Okay? So as far as questions, particularly when it comes to aldehydes and ketones, what I'd be expecting of you is aromatic ring. What does it react as? A nucleophile. So you need to be able to be quick with your definitions so that if you see a structure, any structure, you need to be able to tell me how it can interact. Electrophile, nucleophile, acid, base. All of those definitions need to be on the back of your tongue and ready to come out. To facilitate that, one of the things that we're going to do for the next exam, no, make it even easier, 8.5 by 11 sheet of paper. You can write down whatever you want. Okay? What? It's too difficult to...
I could write all 4 chapters.
I will allow you to use front and back. Whatever you want to write down. Okay? Just because you've got that information doesn't necessarily mean that's going to help you. Okay? Remember, a lot of the questions that I'll ask will be questions that ask you to apply the material. Okay? The application of material is not something that's easily written on a sheet of paper. Okay? So please, you still need to practice the material. This isn't just, yes, I've got all the answers now. You won't have all the answers. Guaranteed. I promise. Okay? We'll see how this works.
You can make it harder now.
Well, we had passed one of the classes in ACs because the teacher allowed that at the last, on the final.
We'll see what happens. Since we're talking about exams too, I will be posting exam scores for the last exam. You'll notice that nearly all of your scores have changed. If you look at the last 3 quizzes that you either got back or should be getting back, you'll notice there were two scores written on them. One is a fraction, because I couldn't do math easily, and one as a number between 1 and 5. The one that's the fraction was the amount of points I added back to your exam 2 score. That took into consideration all of the perfect questions. Okay? So I re-gave you that exam 1. All you had to do was go back through and make sure you learned from your mistakes and you got those points back. If you didn't, then you didn't. Okay? As far as the EAS reaction goes, so we've got our electrophile and our nucleophile. In most reactions, once we get a basic idea of the chemical composition, what we want to do is speed the reaction or change the conditions from something standard. So in our very first case, all we had was an electrophile and a benzene ring. Okay, that's pretty boring. Terribly drawn benzene ring. Okay, so what we want to do is change the structure and see how that affects our reaction or allow us to look at other things. So we can do that by making our electrophile more positive or more electrophilic. Okay? To do so, what we'll end up going through and doing is first off identifying what our electrophiles are. So that's written, in that case, that's written over here. What's our electrophilic atom in our first case? Chlorine. Okay, where is that coming from? Cl plus is not a stable structure. Why is Cl plus not stable? Charge. Why else? What do you know about chlorine? It's electronegative, which means it wants to hold electrons. So for it to be positive, we're going to have something take electrons away from it. How can we get an element to take electrons away from a chlorine atom? It would have to be more electronegative. Chlorine's really, really electronegative, so that doesn't really work. So what do we end up pairing it up with? Chlorine. Okay, we look at a self-bonded structure. Okay, we have to further polarize that structure so that we can get that positive chlorine. To do that, we add a catalyst. In this case, what kind of catalyst do we add? A Lewis acid. Okay, something that will accept electrons. In this case, our Lewis acid is iron trichloride. The electrons from one of the chlorines donates over to the iron. We end up with an unstable intermediate. Okay, that structure further falls apart, and we end up generating our Cl positive, okay, or our electrophile. That can then react with our aromatic ring. Okay, so we're polarizing a bond that was not very polarized to begin with. Okay, what's our electrophile in the second case? What species is positive inside the green box? R. What's our electrophile in this case? R. Okay. R is the standard notation for any carbon-containing compound. So what we're looking at is some carbocation. Okay. To get a positive carbon, what does it need to be attached to? It needs to be attached to something electronegative, something to pull that electron density away. So if we go back to our starting material, in this case we're looking at Rx, where X is a halogen. We can further clarify and put it as a chlorine. Okay, that carbon is now partially positive. It's not positive enough to react with our benzene ring. We have to make it more positive. How can we do that? We can add a Lewis acid catalyst. Okay? That Lewis acid catalyst accepts electrons. The electrons donate into our aluminum. We end up again with our crazy intermediate. The electrons are further taken away from our R, and we end up with our positive. There's our electrophile generation. Okay, makes sense? We've got one more case. It's down here at the very bottom. What's our electrophilic atom in this structure? In our blue case. Pseudo trick question. Our electrophile is typically what charge? Positively charged. Where's our positive charge in this case? On the oxygen. So our gut response is the oxygen is the electrophile. To be an electrophile, it must accept electrons. How many electrons does that oxygen have right now? Greater than 7, less than 9. 8 electrons, which is its octet. Can oxygen expand its octet? No. Can we have another atom come in and share electrons with that oxygen? No. Oxygen is not our electrophilic atom. What is our electrophilic atom in this case? It's the carbon in between. So when you go through to try and identify your electrophiles or nucleophiles, look for charge first, but then look at to see what other things are attached. Okay? Oxygen is an extremely electronegative element. What happens to the electrons in one of those pi bonds? Spend most of their time on the oxygen, which then makes what happen to the carbon? Becomes extremely partially positive. Okay? There's a quicker, easier source for electrons for the oxygen rather than looking outside the structure. It can pull them from the pi bond. Okay? So our electrophile in this last case is actually the carbon, not the oxygen. Okay? How can we generate that? Well, we go all the way back to the beginning on the far left. Okay? There's our electrophilic carbon in the middle. Why would that carbon be electrophilic? What's attached to it? Chlorine. What can you tell me about chlorine versus carbon? Chlorine's more electronegative. So a lot of that electron density is going towards the chlorine. What else is attached to that carbon? Oxygen. What can you tell me about oxygen versus carbon? Oxygen is also more electronegative. A lot of electron density is pulled away from the carbon in that case. What happens to the carbon? Becomes extremely partially positive. To further push this along, we can add, you monkey, we can add a Lewis acid. Again, we get a very similar reaction. The electron density shifts, and we end up forming the acylium ion. Okay? That can be resonance stabilized by taking the lone pair, one of the lone pairs on oxygen, pushing them down towards the carbon, and we end up with that overall structure. Okay? Each of these reagents you absolutely must have memorized, okay, or written on your note sheet, cheat sheet thing, so that you know when you see Cl2 and FeCl3, you know that you're going to add a chlorine atom or do a substitution reaction on a benzene ring where one of the hydrogens is swapped out for a chlorine. Okay? Does that make sense? Getting the general idea of what's happening? Okay. Other electrophiles, we've got 3 more. Instead of reacting with Lewis acids, we can also make electrophiles by reacting with our Bronsted-Lowry acids. Okay, so in this case, we've switched our class on how we're activating these. In this first case, we take nitric acid, we react it with sulfuric acid to make this goofy intermediate. That intermediate falls apart. Oxygen doesn't want to be positively charged, takes the electrons away, and we end up forming our electrophile, okay, or the nitronium ion. Okay? This, I will repeat, is one of my favorite reactions. You will see this guaranteed on the exam in some form or another. Okay? Why? What is this species? This species. This is nitric acid. What is this species? Sulfuric acid. How did nitric acid act in this reaction? So let's compare from here to here. What changed? We write out our formula. We get H2NO3 plus. What changed as we will go from HNO3 to H2NO3 plus? It accepted a hydrogen, which means nitric acid, a strong acid, acts as a base. Okay? Being able to identify the different reactions, those 6 different things, Bronsted-Lowry, acid-base, Lewis, acid-base, electrophile, nucleophile, absolutely are going to show up on the exam. The reagents you will forget. I don't want you to forget the reactivity. Okay? What each of these functional groups can do, and given a reaction, how do they interact? Okay? Can move to the next one, which is a very similar type case. We take another strong acid with itself that can do another reaction to generate a very similar electrophile. Okay, this would be adding a sulfate to your ring. Okay, much less common, you probably won't see that. The very last one, okay, this is also an interesting one, probably has a high priority or high probability of showing up. Okay, we've seen this before. We take an alkene and we react it with a strong acid. The first step of that reaction forms what? You get a carbocation. Where we added that hydrogen to the position that already had the most hydrogens. When we did this reaction in chapter 5, what was the next step? Chloride, our strong nucleophile, attached the positive charge. If we go through and look at the other product formed in this case, okay, we get our carbocation and we get HSO4 minus. What's special about HSO4 minus? Is it reactive? Okay, kind of a pseudo-trick question here. It's negatively charged, so we might say, oh, negative charge, it's reactive. Is that negative charge reactive? No. Why not? Resonance. There's a massive amount of resonance within that sulfate anion, which ends up meaning that that negative charge is extremely stabilized. If it's extremely stable, can it react? No. So that when I add my strong acid to an alkene, I stall at the carbocation. Okay, the reaction can't go anywhere until what happens? What do I have to supply to this reaction to get this reaction to continue forwards? I need a nucleophile. This is positively charged. Okay, how do we stabilize a positive? A negative. What species are negative? Nucleophiles. Okay, so we'd have to supply a nucleophile. In the case of our chapter 5, we're looking at our addition reactions. HCl minus acts as nucleophile. In the case of chapter 9, what's our nucleophile going to be? The benzene ring. Okay. What we've addressed and covered at this point is the electrophiles. Now we can move on to our nucleophiles. Okay. We covered fairly in depth speeding the reaction with aromatic rings or with our nucleophiles. So what we're going to do is go slowly through our slowing the reaction as far as our aromatic nucleophile goes. And then we'll take a look at some problems that introduces both of those concepts. Okay? In each of these cases, what we're ultimately trying to do is see what happens to the reaction when we change our nucleophile. With the nucleophile, we said we couldn't add a catalyst to it because we've got our octet satisfied within benzene. Okay? So we can't force more electrons into that structure. What we have to do is change the elements around it. Which atom is going to be the easiest to change? Your carbons or your hydrogens? Probably the hydrogens. So let's go through and pick a new atom. We're going to do a new reaction here where I'm going to change atom H to atom X. Okay? What's the difference between those atoms? Give me more differences. One's H, one's X. Keep going. What charge? Positively charged. Atom X is positive. Okay? That's a fairly narrow definition. So what I'm going to do is broaden it ever so slightly. Instead of saying positively charged, I'm going to say atom X has less electrons than a hydrogen atom. How many electrons does a hydrogen atom have? One. How do I have less electrons than one? Which would mean what for my charge? Ends up becoming positive. Okay? So if I have an atom that has less electrons than hydrogen, I'm by definition going to be positive. Okay? So what I've got drawn on here is the simplest case possible. What we want to do is evaluate the resonance structures. See how atom X affects the ring. Okay? What's the most reactive position in that structure? X. Why X? You're absolutely right. It's positively charged. How do we stabilize a positive charge? With a negative or electrons. Where do we have electrons? In the pi bonds. So what we'll do is take our pi bond and shift it out towards atom X to help stabilize atom X. What are we doing in this case? We're looking at a resonance structure. Oh, and because I started it, I'm going to draw all the hydrogens on. How many bonds do I now have between carbon and atom X? I have 2 bonds. What charge is atom X? Neutral. Started positive, it's accepted more electrons, it's now neutral. Let's take a look back at our structure. Okay, our overall charge on our resonance structure is what right now? Neutral. Our overall charge on our starting structure? Positive. What does that mean? We missed a charge somewhere. Where's that charge? Top left carbon. Why is that carbon positive? Go back and look at your starting structure. That carbon to start with had its full octet. We took an electron in that pi bond that initially came from it. We took it away and we put it somewhere else. It's now lost electrons. It has to become positively charged. Okay, I didn't draw it out for any of the others, but let's go ahead and do it again. Let's look at another resonance structure. Positive charge. Is that stable? No. So what are we going to do? We'll move electrons. Oops. Here. Now I'm going to stop drawing our hydrogens. Where's our positive charge? Now on our bottom. Positive charge stable? No. So what are we going to do? We're going to do more resonance. We end up with our final structure. One of the things that I ended up abbreviating in the previous cases is instead of drawing out all of those resonance structures, is I ended up drawing our aromatic ring and I went through and just put positive charges on it. Okay? What I'm trying to show in that case is that we've got a hybrid structure. So we could go through and try and draw all the electrons being shared all the way around that. We've put positive charge at each of those positions. And technically, we even have it up on atom X. Okay? Why is that relevant to us? Our aromatic ring acted as what in the reaction? What charge does a nucleophile need to be? nucleus loving. Nuclei are positive. How can I be attracted to a positive charge? I have to be negative. So if we go back and now look at this hybrid structure, okay, do we see any negative charge? No. Would we expect this structure to react as fast as hydrogen? Or as our benzene ring? No. We've taken electron density out of the ring. For our reaction to react faster, we needed more electrons in the ring. So what we've done is slowed the reaction. We can refer to this, or atom X in this case, as a deactivator, because it has slowed our reaction down. Okay? Taking a step further, we want to then go through and classify where our electrophile, or predict where our electrophile would substitute in this case. Okay? Could it go to positions 2 or 6? So that would be the ones directly opposite atom X, because atom X would be started with our number 1. So 1, 2, 3, 4, 5, 6. Would we expect 2 or 6 to be active? Why not? It's positively charged. There's no electrons there. How about position 4? No, why not? Positively charged. What's the only position that doesn't have a positive charge? 3 and 5. So we would end up likely seeing our electrophile substitute to the 3 or 5 positions. So we can say atom X in this case is a deactivator that directs, or that is a 3-5 director. Some people don't like numbers, so instead we can refer to it as the meta director. Okay, so we can refer to both positions 3 and 5 with one term. Okay, does that make sense? Questions about that? Okay, so let's go through and kind of summarize what we've kind of seen here. So let's take a look at our very first case. The top one there. What can you tell me about atom X? Has a lone pair. So atom X has more electrons than hydrogen, than a hydrogen atom. If that is the case, what do we see? Or how could we classify atom X? If it has more electrons, we can take those electrons and push them into the ring, which then means this carbon has too many bonds, so we take the double bond and we put it on that carbon. What charge does that carbon build? Negative charge, meaning my ring has become negative. What does that mean about its nucleophilicity? It's more nucleophilic. What would I predict for the speed of that reaction? It should be faster, so we'll refer to it as an activator. If we go through and push out the rest of the resonance structures for that, where else do we see charge build? So we've got the 2 position. Where else? 6 position. Good answer. And the 4 position. So we could call it a 2-6-4 director. It's an awful lot of letters. So what can we call it? And I'm going to change this real quickly here. We'll say a 4-2-6 director, para, ortho director. Why did I swap the order on that? We prefer to see the para substitution, or substitution over the ortho. Why would the para substitute over the ortho? If we look at this ring having to react, this double bond has to come out. Okay, what's near it? What is atom X? A lot of electrons. So what happens when I take the electrons from my pi bond and try and get them near atom X? They repel and they go right back into the ring, which means ortho's not as reactive. How about the para condition? If I try and go out this direction, what do I have to get by? Not quite. Hydrogen, which is effectively nothing. Which position is more active? The para position. Okay? When we're looking at our ortho-para directors. That is a really small eraser. Okay? We're going to get to the whole weird thing in a second. Questions about our activating abilities? Okay. Let's look at atom X now down below. What can you tell me about atom X now?
Negative.
It's what?
I had my glasses off for a second.
Has less electrons than a hydrogen atom. Pretty much the only way we can do that is we have to have a positive charge. If we go through and look at our resonance structures, we can push electron density out of the ring, which means what builds on our carbon? Positive charge. If our ring becomes positive, what happens to its nucleophilicity? It decreases. So we would expect a slower reaction. We now have a deactivator. Yep. Okay. That will put a positive charge at our 2, 4, 6 positions. What's the only position left to react? Our 3 and 5 positions, or our meta.
Is it just every other one? Like, I just don't want you to go through the whole thing, because I know, like, if you
What do you mean
drew
every
them
other
all
one?
out, you would understand, like, which ones.
So when we're referring to our 2, 4, 6 or 3, 5 meta orthopara, it's all referring back to some substituent on the ring. So in this case, we're referring with respect to atom X. Atom X, by definition, is at position 1. Why do we name it as position 1?
Because it's a 1.
Priority in what?
The carbon chain.
Nomenclature. Okay. Our numbering system ultimately comes back to nomenclature. And if I was going to name this, it's 1x benzene, where X is at position 1. I can then go through and count out the rest of those and number those out.
I get that.
And we end up defining position 3 and 5 as the meta positions.
I think what she's saying is how do you determine where the charges are going to land?
Is that what it is?
Yeah. But
Charges, where the charges are going to land goes back to resonance. What you would need to do is draw the resonance structure for each of these. Does that work?
Yeah.
There's not a generalization like every other one or whatever. It has to
I'm
be
not going to give you a generalization on that.
Right.
But yes, you do end up noticing in every other one pattern fall out of that.
Because it's looking, because it's a nucleophile that's, or it's whatever's going to attach to the electrophile is looking for.
You're lucky. I know. So, here's our more difficult structure. Benzene ring with bromine. Okay, just because you said that.
No. I hate all halogens now.
Well, I can't fix that. Atom X in this case is now a halogen. What would we expect or predict? So we go through based on our rules. Atom X, does it have more electrons than a hydrogen atom?
Yes.
Absolutely. Does atom X have less electrons than a hydrogen atom?
No.
Not really. So let's go based off of our red structure. We could expect the electrons to donate in And we could expect something along these lines with our resonance structure. Can you guys see that? Okay. Which would suggest we have electrons where? The ortho positions, and also our para, if we push the resonance all the way around. Okay? So as far as where we would expect the electrophile to go, we would expect our halogens to be para-ortho directors. Anybody have any problems with that resonance structure that I drew? Particularly the bond that's about to get highlighted in red.
Chlorine only wants one bond.
Chlorine only wants one bond. Interesting. So we've gone through and shown a resonance contributor that suggests that we get electrons at our ortho and para positions, but in the process of doing so, we've made a highly unstable cation on that chlorine. What are the odds that this is going to be a good resonance contributor? Not very likely. Taking a step further, what's the comparison between chlorine and carbon? Chlorine's more electronegative than carbon. Is chlorine ever going to donate those electrons to the carbon? No. In fact, what's it going to do? It's going to take the electrons away. So if we go back to our original structure and we start to take electrons away, what happens to that carbon? Which means our ring is now positive, which would suggest deactivator. So what's the answer? It's both. Your halogens will act as deactivators because they're electronegative. They will pull electron density away from the ring. But because they have those extra electrons, they do an orbital overlap, which I'm not going to draw, but that's the official description, with the pi system. That orbital overlap increases electron density at the ortho and para positions, meaning your halogens end up being para-ortho directors. Okay? Every other functional group, every other atom X fits nicely into either has more electrons or less electrons. The only ones that don't are your halogens. Okay?
So
Yes.
it can be both, but you're going to assume it's going to be the para-ortho, is that what you just said?
By both, I mean both of these rules hold.
Right.
It is a deactivator and it directs to the para-ortho position.
So it slows down the reaction.
It slows the reaction, but our electrophile goes to the para-ortho position. So it's a mix of both the activators and deactivators. Okay? It would have been nice if we could have grouped all activators together with para-ortho directing and all deactivators together with meta-directing, but we can't. Thankfully, the only one exception is dealing with our halogens. Yes?
So what about on this that you were showing?
Yep.
On here that the bromine went, or it reacted regularly, but you didn't say anything about that.
Let me try that again. Before we start doing examples with our multiple substitutions, let's go through and actually start to apply that activating, deactivating thing. So what we're going to try and do is decide between these groups whether we would expect them to be faster reactions. So if they're faster, atom X will have more electrons than hydrogen. If it's slower, it would have less electrons than hydrogen. So let's go through and look at these cases. Give me a different color. We're going to look at an OH attached to the ring. Do I need to draw the aromatic? I'm going to draw them. Change my mind. No, I'm not. That's going to be a lot of rings.
Make us.
Okay? So we'll put on the ring in the first case, and then I'm going to stop doing that. I'm going to need more space for that next one. Just put a little squiggly line between it to signify that we're going to the aromatic ring. Then have a nitrogen, carbon. Change my mind. Let's get rid of that. What's the next one? And sorry for the dead. Now that we've got all our options on here, we want to go through and rank these according to which one's the strongest activator. So what do we got? 1, 2, 3, 4, 5, 6. 1 is our biggest activator. 6 is our smallest activator. Get it? Because I wrote it smaller? Okay, come on. I gotta try and get some smiles. You guys look so depressed. Okay, so we need to go through and try and classify these as best we can. Okay? So if it's an activator, what do we need to look for? We need to find atom X with more electrons than a hydrogen atom. So to start off with, I want to go through and label atom X in each of these cases. What's atom X in our first structure? What's atom X in our next structure? So that's exactly the question I was fishing for. What we're looking for is only the atom immediately bound to the ring. That's the only thing that we're comparing in these cases. We don't care about the rest of those atoms. They can have a secondary effect on our atom X, but we're primarily concerned about the atom immediately attached to the ring. So good question. Okay, you told me nitrogen, right? What's the next atom? And our carbon. Okay, so now that we know what atoms we're looking at, we need to go back through and start to rank these. How should you start any ranking problem? Not a bad choice. That's not where I was going, but that's a good idea. Let's put in the implied electrons. So oxygen has 2 lone pair. How many does nitrogen have? How many does carbon have? How many hydrogen? Chlorine? Come on now. I didn't say it.
You should have.
And our last one? None. Okay. So now what can we do?
Just start
Start somewhere. Pick any 2 you want. There's no way that you should be able to, or at least I wouldn't expect you to be able to, immediately drop rankings on every single one of these. So pick a position to start and pick another one. You want to start with hydrogen? What's your next atom? And then nitrogen. So let's compare our hydrogen structure. So here to here. So hydrogens are 0 point. So let's take a look at atom X on our nitrogen. Does it have more electrons than hydrogen? Does it have a lone pair? Yes. Nitrogen, yeah. Does it have a lone pair? Does it have more electrons than hydrogen? Yes. So should it be more active or less active than hydrogen? More. So what we can go through and do, and instead of bubbling in exact answers, we can say 1, and for the moment we can do 2. Okay? Because we know it's smaller. Okay? Now what should we do? Pick another one. Okay, so let's pick the carbon. Which carbon? CH3. What do we want to compare that to? We can compare it to pretty much anything we want, but a good place to start would be to something that we've already labeled. Okay, so we'll compare it either to our nitrogen or our hydrogen. I heard nitrogen first. Okay, atom X has more electrons than hydrogen. Nitrogen has a lone pair. What does carbon have? Nothing. Which one's more activating? Nitrogen. So nitrogen is still 1, our carbon is 2. We compare carbon to hydrogen now. Which one has more electrons than hydrogen? Carbon. How do you know carbon has more electrons? Could go as far as more bonds. Lower on the periodic table. Okay, it's got more electrons, which means what do we need to do? Change hydrogen to 3. What do we do now? Go to chlorine. Does chlorine have more electrons than hydrogen? Which would suggest it's an activator. Except it's a halogen, so it's a deactivator, which means it's less than hydrogen. So at this point, we would just say 4. Do we have to compare the chlorine back to carbon or nitrogen? No, we're already at our extremes. So next. Where are we going? Left, right. Okay, that's left, just so you know. Oxygen. So if we now compare oxygen to what? Okay, oxygen to nitrogen. Do they both have more electrons than hydrogen? Yes. So now it's going to get tricky. So they're both activators. How many electron pairs can we ever donate at any given time? 1. Okay, which means when we look at oxygen, we're only looking at one lone pair. We ignore the other one. So in this case, we've got 2 atoms, each with one lone pair. Which one can donate better? Why do you say nitrogen? Less electronegative. That's not a bad option. Is there something else that we should consider? What's special about this oxygen? What's that? True? Keep going. It's partially negative. How is it partially negative? It's drawing electron density away from that carbon. So that carbon becomes partially positive. Does it want to be positive? No. So where does it go? Or what does it need? Electrons. Where do we have electrons nearby? What charge builds on that nitrogen? We get a partial positive charge. Which has more electrons to share, oxygen or nitrogen? Oxygen in this case. Okay, what does that mean for our ranking? Oxygen's higher than nitrogen. So oxygen needs to be 1, nitrogen needs to be 2, which means really? Okay. That's why I said really. So let's take a look at the very last one. Carbon. More electrons than hydrogen? Yes, but it's partially positive because of the electron withdrawing oxygen. We generate a partial positive on that carbon, which means it's a deactivator. Okay? Our chlorine was somewhere in the middle, so where would we put that last one? 6.
Why
Okay.
is it more of a deactivator than
Chlorine is a deactivator, but it directs to the ortho-para positions, so it's still slightly more activating than our aldehyde or our carbonyl. Okay? So the idea is to evaluate that atom, see what things are attached to it, and push things around. See how things change. Make sense? Yes?
So if our nitrogen compound was just NH2, how would it compare to OH?
So let's change that around to just a hydrogen. So now when we compare, both of those have a single lone pair. Which of those two is more willing to share electrons? Nitrogen. So what's our order?
So it would be oxygen 2, nitrogen 1.
Those two would swap. Questions about that? Okay, so let's take a look at some multi-substitutions. So if we start with, benzene, pull this straight from your quiz 8. Except I write really big. So we're seeing a new notation here, 1, then 2. This means there are 2 steps in this reaction. We've just decided to condense it into 1. I want the final answer. Okay? So what would be our first step? So we can even do the box. Here's where our final answer needs to be. Our first step is going to be to react bromine with our aromatic ring. So what we could go through and do is, if I actually get it posted, the list of all the reagents, or you could flip open your textbook and look for what BR2 and FeBr3 does. What does it end up doing? Does a substitution reaction, not addition. I keep saying it too. Which hydrogen does it substitute for?
Any of them.
Any of them. Why? They're all the same. Okay? Then we move to step 2. What is step 2 going to do? It adds the NO2. Okay? And it's going to do a substitution reaction and substitute for a hydrogen. Are all of those hydrogens the same now? No. So we now need to decide which of those hydrogens is going to be the reactive one. We'd have to go back and evaluate the effects of atom X. What is atom X in this case? Atom X is our bromine, which happens to be a halogen. What do halogens do? They deactivate and they're para-ortho directors. Where should our nitro go? To our para position. We could now draw our final answer. Why did I draw the NO2 like that? Trying to show the atom connectivity as best I can. The nitrogen is the atom that attached to the ring, not the oxygens.
Isn't the para the one at the bottom?
So you have to remember where your positions are. Para's not on the bottom because I could flip the structure. So it's opposite of where our group is at. So the para is completely opposite. You can go around and do all your numbering if you want as well. Okay, you can't just say bottom, top, sides. Okay? Questions about that? What happens if instead of doing that order, I said I do our bromination second and our nitration first? What happens now?
The nitrate directs the bromine.
So in step 1, I end up adding the nitronium ion. Where does the nitronium ion add? Or substitute, sorry. Good answer. Anywhere on the ring, it doesn't matter. Step 2 is adding the bromine ion. Yep, still doing it. Substituting the bromine. It's not an addition reaction, it's a substitution. Okay? Where does the bromine now go? So now we have to go back and identify atom X. What's atom X in this case? Nitrogen, but this is where it gets a little bit tricky. As it's drawn on there, can you tell anything about its bond structure or its charge? Okay, probably not, so you'd need to draw out your Lewis structure for this. When you draw out your Lewis structure, find that. What can you tell me about atom X? It's positively charged, so it is a deactivator and a meta director. So in the case of our product, our nitro was added first, our bromine was added second. Where does the bromine go? Our 3 or 5 position. So the order in which we do the steps of adding our electrophiles or reacting with our electrophiles makes a huge difference in what our products are. Okay? So you have to be very careful with what order you're adding each of these things on. Yes?
You said you'd tell us why it wasn't both. 3 and 5. You said that was a reason why it went.
Whenever I ask you a question like this, I'm going to expect you to do one substitution, not more than one, unless I specifically say do 2 substitutions. In this particular case, the main reason why we don't do more than one would be nitro is what kind of a group? Deactivator. What kind of a group was bromine? Deactivator. What have I done to this ring? Very, very deactivated. For it to react a second time, I'd have to react it with a very positive bromine. I'd have to somehow really tweak the chemistry to force it to react. Okay? Just for the heck of it, draw this one up real quickly. What do you think? How easy would it be to make this compound? Not. Good answer. Why? All?
Oh, no.
That methyl is activating, but what can you tell me about each of those nitros? They're all deactivating. So as soon as I add one nitro to the ring shuts down, becomes less reactive. Okay? Let's say somehow I force the reaction to work and I get that second nitro on. But now what's happened? It's even further deactivated. Okay? Why is this structure kind of interesting? You want to try and name this one? What's this functional group referred to as? Nitro. What is this piece? How many nitros are there? 3, known as trinitrotoluene, also known as TNT. Okay. So it's an explosive compound, not particularly stable. Okay, other things that we could go through and do. Let's see. I didn't think all of these through, unfortunately, so we'll have to see what happens. Oh, I lied. I double lied. All I did was erase, though. Benzene to, my best guess, ethyl toluene ketone? Something along those lines. What do we need to do? In fact, this reaction isn't going to work, but that's fine. Still go through with what reagents we've got to add to this. And we'll end it on this. So what pieces do we have to add? So somehow or another we have to add CH3 and how can we make those? This needs to be positive too. This last one, the bottom one, is known as the I have no idea how to spell it, actually. The acylium ion. Remember? Everybody had a good laugh, or at least I had a good laugh about that one. How would you figure it out? You got to go back to your reagents and try and figure out where those came from. For this bottom one, we're looking at, or sorry, that's not the bottom, is it? That's the top one. And our bottom one, yes? Which one do we add first? Substitute first. Substitute. If we put the top one on first, we generate this as an intermediate, right? Atom X. What is atom X in this case? Carbon. Does that have more electrons or less electrons than hydrogen? More, which means it directs to our ortho or para positions. Is that where we want our ketone to go? No. Which one has to be added first? The acylium has to be done first, then our other one. Does it make sense? Was that a yep or a nope? Oh, okay, good. So that will be the end of our benzene chapter. I will very, very quickly go through our aldehydes and ketones material from chapter 13, looking at carbonyls. It's just nomenclature. I will get those problems posted tomorrow, probably with this lecture.